So we're gonna start lessons on Lie algebras, and our goal to this course is to give a complete proof of the classification of Lie algebras with one of the works of Cartan. And in this work, inspired by Wilhelm Killing, gives to us complete classifications of complex semisimple Lie algebras. But before we go on this classification, we gotta remember we gonna work, and I want to introduce some basic concepts on the algebras. Start with defining what is a Lie algebra. What is a Lie algebra? A Lie algebra is a vector space, let's say G, and its notation is D in Gothic. In many aspects, we're gonna use this notation in Gothic for represent some Lie algebras, and let G vector space. Lie algebra it's G vector space over any field K. In our case, K it's equal to C, and sometimes, for give some example, I use K is equal to R. But for our classification, all the algebra is over the complex field. So a Lie algebra is a vector space G over field K with something like multiplication that we know in the rings. So a ring is set with two operations, sum and multiplication. That operation has some properties, some nice properties, and we have some multiplication. But this multiplication we're gonna call to bracket. It's an operation in D times G to the set D. This bracket wrote the following conditions. One is antisymmetric. And what does this mean? This means that Lie bracket of x and y is equal to minus x and y. This condition can be replaced by this condition. The Lie bracket is x by x, and if you think a lot, I think that you can prove that two condition is equivalent. So letting commenter your solution for this property. And two, the Lie bracket is attain the condition named by the Cauchy, the Jacob identity. is Jacob identity. Say that x bracket I bracket z plus x bracket y, this bracket z plus x bracket z bracket I it's equal 0. We have some problems in this order, but this unsymmetric condition can help us to say that this condition is equivalent to say that the sum of cyclical permutation is ever equal to 0. And this is the algebra, and we have some example. One of these example is the vector space R3. In R3, with the vector product, it's a Lie algebra because R3 is a vector space over R, and the condition of this bracket with the vector product is some difficulty, and I haven't proved yet. But we have other example. Let's say example 2. This example is a matrix space. The multiplication is the sum and the scalar product that we will make that space GLN over R or over C is the same as we know in the sum and scalar product of matrix as well. But the product, the Lie bracket, we're gonna to define by x bracket I is equal x times I minus I times x, where x times I and I times x is the usual matrix product. And this is Lie algebra, and the proof I don't want to prove this. This is Lie algebra. And in the general case, if A is associative ring, that is, the multiplication in this ring is associative, so defining Lie bracket as x times I minus I times x, we have similar results in the matrix world. The same is an associative ring with associative algebra because the ring don't necessarily have the scalar product. This is gonna be a Lie algebra 2. Lie algebra as well. Sorry. And what is some other interesting examples? One of most important example of Lie algebra is the Lie algebra SL and C. And this Lie algebra is defined by all matrices A in GLN over C, such that the trace of the matrix A is equal to 0. It's very easy to see that SLN over C is a vector subspace of JLN over C. It's very simple to see that because the sum of matrix with trace 0 it's a matrix with trace 0 2, and the scalar product is very simple to see that hold this condition too. But to verify that x I minus x, to verify that x bracket I is in SL1, you need to prove that x times I minus I times x have trace is equal 0. Is not too difficult to see, but you have made some computations to conclude it. Other examples is a special orthogonal. It's SCO, an O matrix with what's condition, which is X transpose I is equal Y transpose X, and some other examples. The algebras is very important because one can associate to every semisimple Lie algebra a Lie group. Let's say G. This Lie group have a geometric structure because these are manifolds, and we can classify all simple Lie groups with this relation one by one, because one can classify all Lie simple algebras. An important concept behind the Lie algebra is the one specific linear transformation that we can construct with the Lie bracket. That's linear transformation is called by adjoint transformation. It's a linear transformation from G over G, and we take this adjoint transformation depends of an element X, and this leaves I in the bracket X bracket I. And this is a linear transformation because this bracket is bilinear transformation. So if you fix X in this coordinate, so the properties of linearity is induced by the property of bilinearity of the bracket of the Lie bracket. And this adjoint transformation leads us to give some beautiful theorems like the Lie theorem and evidently the angel theorem. That's which help us to study some of elements in the Lie algebra called by nilpotent elements. In some sense, the study of Lie algebra is generalization of a study of vector space, and there is a theorem. There are theorem called by the one big theorem. I don't remember the name right now. Adolph's theorem says that every Lie algebra is a subalgebra of a matrix algebra, and is a very deep result in Lie theory, but it's very hard to prove, and we're gonna make it proof of this theorem because it's very hard. But we can define one strategy to classify all the algebra, all semisimple Lie algebra in this next video.